so for chapter 20, we talked at length about the idea of heat engines, their efficiencies. And we said if you run them backwards, you get refrigerators and ACs. We haven't talked too much about entropy yet, so today we'll introduce entropy. We did talk about the second law that says that you can't have a 100% efficient engine. And then we did two specific examples of heat engine, Carnot and the Stirling. The Stirling was isobaric, so it didn't have the isothermal part. And then it had it had the isovolumic, and then it had the isothermal, then it had isovolumic. So I remember saying, oh, it's an easier version of the Carnot because you don't have to worry about adiabatic, you don't have to worry about PV, the gamma is a constant. So it's just isotherm, it has the top, the bottom, and then it's got the isotherm, and then it's got the isovolumic. So it's nice to have a drawing like this to show what the PV diagram of the cycle looks like, and also to draw a little wiggly sign showing where the heat coming in and where the heat that's being dumped. So here, heat is coming in here, Q in. For adiabatic, there is no heat exchange with the surrounding. So you're putting in heat in this process, in the isothermal process, and that's what's helping run the engine. And then here you're dumping the heat back out. Remember, the second law says that you can't just put heat in and do work. You have to dump heat out, otherwise you would have a 100% efficient engine. So here, Q out. Okay, and it turns out that the Carnot cycle is the best efficient cycle that works between two temperature reservoirs. And then we derive the efficiency of this E Carnot is 1 minus T cold over T hot. And so the Carnot efficiency is the highest efficient engine that can work between two different temperatures. Highest efficient engine that can run between two temperatures. And the Carnot efficiency is not even 100% itself. So depending on the T cold and the T hot, the Carnot efficiency is going to run something like, let's say, 50% or 40% or 60%. But most engines are not even going to, their real efficiencies are not even going to equal to the Carnot efficiency, because maybe they're not even running the Carnot cycle, or even if they are running the Carnot cycle, there's heat losses that they're experiencing. So that's going to cause their efficiency to go down, you see. So then you got the Stirling cycle here. The heat is coming in here, Q in, but heat is coming in also here in isovolumic. Q in, we can call it Q in 1, Q in 2. And then these two, you're dumping the heat out. Okay, so it's these two that is making the engine run, and then these two, you're just dumping it back out. And then the efficiency for this turned out to be a much more complicated equation. Rather than trying to necessarily remember that equation that we derived, we can just remember the processes, and then if we're given a problem like this, we can just start from the beginning and calculate, okay, how much heat did it do, how much work did it do from all of this, rather than trying to remember that equation. It was something like ln of V2 over V1, and then it had some T in there and stuff like that. So let's see some other famous ones. This is the Otto cycle. So you see here the gas-only cycles, Carnot cycle, Stirling cycle, internal combustion engine, Otto cycle. Okay, so what does that look like? Otto cycle. It kind of starts here, but that part doesn't really matter. Process 0 to 1 called the intake stroke. From 0 to 1, and then it goes like this. So this is the cycle that, what does it say? That gas engines run, gasoline engines. So Otto cycle. So this one going from 1 to 2. So is that a isothermal, or it probably adiabatic, because if it was isothermal, it would be exactly like the Stirling engine. You know, isothermal, isovolumic. Then what would the difference be between Stirling and Otto? So it must be adiabatic, but here it's not. It's the compression stroke. This is called the compression stroke. Then ignition stroke. You ignite. The spark plugs ignite, and then expansion stroke, and then idealized heat rejection, process 4 to 1, and then process 1 to 0, exhaust stroke. So the compression stroke here, going from 1 to 2, isentropic compression. They use a different word, but I'm pretty sure it should be yeah, there you have it. So they use a word isentropic, but I haven't seen that word that often, but it's the same thing as adiabatic. So you got the intake stroke, which the intake and the exhaust stroke kind of cancel themselves out. So they don't really do much, but so you intake is the gasoline comes in, and then you do the compression, adiabatic. So adiabatic. And so with any of these strokes, it really doesn't matter for the sake of calculating the efficiency of the engine or the work done by the engine. It really doesn't matter where you start. You can start at this corner, then go like this, go like this, go like this, go like this, or you can start at this corner, go like this, go like this, go like this, go like this. So it's not like you have to memorize, oh, in real life, where does the process actually begin for me to do the calculations right? You can start any corner and still do as long as you go a complete cycle around, you still can do the calculations correctly. In here, it starts here, then you do an intake stroke, you go up like this, but then again, to do the calculations, you can start any corner. So you go adiabatically like this, then you go isovolumically up, so you go back down adiabatic, then you go down. And again, you could start any corner. Okay, so where would be the heat here coming in? Adiabatic, no heat exchange. Here is the only heat coming in. Q in. Here, no heat exchange. And then here you dump the heat. Q out. And that's it. Okay. Then the rest, you just do the numbers and calculate it, okay? By the way, in this class, we're gonna typically focus on pressure versus volume graphs. But in reality, you can graph anything versus anything else. You can do pressure versus temperature graph. These are called state variables. Pressure, volume, temperature, and then the next thing we're gonna define is entropy. So state variables. In other words, they're variables that define the state of a gas at any instant. The temperature of the gas, the volume of the gas, the pressure of the gas, and the entropy of the gas. So you could do any graph. Pressure versus volume is the typical one, but you could also graph pressure versus entropy, pressure versus temperature of the gas. You see what I mean? Pressure versus entropy, pressure versus temperature. You could switch them if you want. You could do temperature versus entropy. You could do entropy versus temperature. You could do entropy versus pressure. You see what I mean? So, of course, pressure versus volume has a particular interest because the area under the graph is the work done by the gas. So, and the units of it is joules. So things that are joules and whose area means work is a little bit more interesting to us than other stuff. But you can kind of see here when they're showing you the PV diagram of a Otto cycle, next to it they also do a different diagram. Okay, so what diagram is that? On the left is the one we focus on, right? It's pressure versus volume. What is this? Temperature versus entropy. You see, of an Otto cycle. Temperature versus entropy. Does the area under that graph have any meaning? Well, we'll see once we define entropy, whether that area has meaning. So it kind of looks like pressure versus volume, but it's almost like a mirror image of it, right? This part looks like it goes there, and then this part looks like it goes there, almost like a mirror image. So you could kind of do that with any of these graphs. You see PV diagrams. PV is the most common, but then you also see sometimes temperature versus temperature. I've seen a lot of times temperature versus entropy cut. Okay. Okay, what else? Diesel cycle. How does that one work? It's interesting that the diesel will have a separate cycle. Oh, so isobaric. That's the first one that has an isobaric one. None of this has isobaric, so it has isobaric. Then it's got isentropic. That's the one that same is adiabatic. Adiabatic. It's just, I guess, a different word. So then it goes like this: adiabatic. Then isovolumic. Then adiabatic. So it's kind of looks like Otto cycle. Like this, then adiabatic, then isovolumic, and then adiabatically goes back. Adiabatic. So where does the heat come in for this one? Q in. So heat would come in here. No heat here, and then Q out here. That's it. pressure versus volume. There might be a reason why they did that for diesel. This is for gasoline, and that's for diesel. So I guess for this one, you're going up higher, and then you're going this way. You see the difference? Here, it's like going like this, and keep going until you get to the same pressure. Then go isobarically like that, you see. Now, with any of these, you could also maybe do a video, let's see. Actually see the stroke.
The mechanism is going through a cycle, and after being in state, it's not moving. Point and it goes to zero. And so with that, we have the equations for both Q and
They're deriving the equation.
These relationships here, and let's work them into this relationship up here and see what we obtain. And I'm not going to go.
I want to talk about the modeling of combustion engines with the Otto cycle. Combustion engines are probably most familiar to you as the power source for many automobiles. So we'll bring out a vehicle. Now I'm cheating a little bit. This is a bus. Most buses probably run on diesel engines and are best modeled by the diesel cycle. But hey, you try drawing a car sometime. It's not easy. So let's take another bus. What I really want to know, though, is not what the bus looks like, but rather how its engine works. And we're going to focus on one cylinder within an engine. So we'll model that just as a piston. Really, the Otto cycle is just a complicated piston process. And while I'm talking about it, over here on the right, I'm going to label states and processes
Well, see,
on
they're doing
PV
temperature
and
versus
TS plots as
entropy
we go.
also.
So let's start with state 1, which we know has to be a pretty big volume. That piston over there is pretty expanded. So we're going to start at state 1, and what we're going to do is compress the piston until we get to a state 2 on both plots. So let's do that. Okay, we compress the piston, and what we're doing is compressing it isentropically, as you can see from the TS plot. So we didn't change the entropy of the system. We did change the pressure and the temperature and the volume, though. All right, if we want to model this, well, we need to know something about how that work is associated with other quantities.
So the reason why adiabatic is sometimes also called isentropic is because for adiabatic, if no heat is exchanged, the entropy is constant. The disorder of the system is not changing. Entropy is a measure of disorder, you see. So if this is adiabatic, then the temperature versus entropy graph, right? The entropy is going to be constant for the adiabatic. You see, you can kind of see here. The entropy is constant, the temperature is increasing. Here on the PV diagram, the volume is decreasing, and adiabatically the pressure is increasing. See, so that's why maybe it's good why they do temperature versus entropy and PV, right? So what did they do? They compressed it adiabatically. Notice no heat came in or out. Okay, so let's see what else happens. That's called the compression stroke.
As usual, when we're modeling complicated cycles, we're going to ignore kinetic and potential effects, so that simplifies our lives a little bit. In this case, well, remember, heat transfer for a reversible process, including processes within the Otto cycle, would be represented by area on a TS plot. There's no area under that vertical line, so that automatically tells us that actually all we need to worry about is the work, and that W over M will just be the difference in internal energies. Okay? So W over M is the difference in specific internal energies of state 2 and state 1 for that process in the Otto cycle. Okay, so we compressed our piston. Now we're going to go to state 3. State 3 is going to be at the same volume, but we're going to transfer some heat. So what we do is we transfer some heat, but we don't change the volume of the piston at all. And as we transfer heat, we do increase the pressure, we do increase the temperature and the entropy. So you can see that state 3 is higher up on the PV plot, higher up and to the right on the TS plot. But we didn't.
See that? So that's where the ignition stroke is called. You ignite it like this, so the volume stays constant, and then the pressure increases, the temperature increases. The temperature increases, and then the entropy increases, because the molecules are now moving faster, so there's more disorder. You can see.
Didn't change the volume of the piston cylinder at all. That means that it's a vertical line on the PV plot. No work was done on the piston. Okay, so the expression for that, since we know the work is 0, must just be that actually now it's Q over M that's going to be the difference in specific internal energies. Okay, you may see a pattern here. To get to state 4, we're going to execute an isentropic expansion. And of course, isentropic means that it'll be a vertical line on the TS plot. We'll go down and to the right on the PV plot. Now in that case, we know that work was associated with this. For one thing, the piston moved, but for the other thing, there's area under that curve on the PV plot. And we know that there's no heat transfer once again, because we have a vertical line going from 0.3 to 0.4 over on the TS plot. So the expression associated with this, exactly as you would assume, would be the difference in specific internal energies for 3 and 4. All right, final step, well, we have to get back to state 1. This one is again going to proceed at constant volume, and what we're going to do is transfer heat away from the piston cylinder now. So we do that, and we get back to state 1. Okay, obviously we change the entropy, the temperature, and the pressure, but not the volume. So the expression for that, using the same logic, is given by Q over M equals the difference in specific internal energy at state 4 and state 1. And just to be clear, the reason all of those relationships at the top are so simple is that for any process you pick, let's pick process 2 to 3 arbitrarily, you're always guaranteed that one of the two processes on a PV or a TS plot is going to be a vertical line. Remember, when you have a vertical line, that automatically means that in the case of a PV plot, the work is 0. In the case of a TS plot, it would mean that the heat transfer is 0. In this case, for process 2 to 3, work is 0. That means we just have to focus on the heat transfer. The only thing it can be related to is the specific internal energy, because we said everything else was ignorable. All right, putting all these expressions together, which works in much the same way as the Rankine cycle, we get an overall thermal efficiency for an Otto cycle that is eta equals all this stuff, which simplifies nicely to 1 minus U4 minus U1 divided by U3 minus U2. So if you can get the specific internal energies for any Otto cycle problem, you're in great shape.
Go through all the details.
Now let me actually see an engine.
The Otto engine is a combustion engine and is considered to be a technological milestone of human thought. It was named after its inventor, Nicholas August Otto. Otto engines are used in motorcycles, cars, and other vehicles. This animation explains the Otto engine as a 4-stroke engine. This engine is composed of a piston that moves up and down in a cylinder. The highest point the piston can reach is called top dead center. The lowest point it can reach is called bottom dead center. The volume between both points is called engine displacement. The piston is connected to the crankshaft through the connecting rod. The crankshaft transmits the rotational movement to the gearbox and consequently drives the wheels of a car or motorcycle. Two camshafts are installed on top of the cylinder, which control the intake and exhaust valve. The camshaft is connected to the crankshaft through a belt. More often than not, the crankshaft to camshaft gear ratio is 2 to 1, which means that for every 2 revolutions of the camshaft will rotate only once. An Otto engine has a spark plug that uses an electric spark to ignite the fuel charge. A four-stroke Otto engine is an internal combustion engine in which the piston completes four separate strokes. The first stroke is called intake stroke. Here, the intake valve is opened by the rotating cam. The air-fuel mixture is sucked into the cylinder.
Remember, the intake stroke is this one. So if you really want to understand, you got to really go over this. The intake stroke, it goes like this. That's the intake stroke. You're taking in the gas. Okay? So on the PV diagram, the pressure is staying constant and the volume is increasing. Then you're going to have the compression stroke, ignition, expansion, and then exhaustion, I believe. And then you go back to, you open the valve, let the gas out, then a new gas comes in. So let's
that uses an electric spark to ignite the fuel charge. A four-stroke Otto engine is an internal combustion engine in which the piston completes four separate strokes. The first stroke is called intake stroke. Here, the intake valve is opened by the rotating cam. The air-fuel mixture is sucked into the cylinder. The second stroke is the compression stroke. The intake valve is closed and the air-fuel mixture is compressed to a high degree by the piston. The higher the compression ratio, the more mechanical energy the engine can squeeze from the air-fuel mixture. Higher compression ratios, however, make self-ignition more likely. The third stroke has been named power stroke because this is the process where power is produced. The air-fuel mixture explodes. The force created by the explosion causes the piston to move down. The fourth stroke is called exhaust stroke. In this stage, gases remaining in the cylinder are removed from the cylinder through an exhaust valve. The crankshaft transmits the rotational movement to the gearbox, and the driver can drive. Often, engines of today feature more than one cylinder to power cars or motorcycles in order to increase speed and smoothness.
now the diesel one.
An internal combustion engine transforms the chemical energy in fuel to mechanical
At a
energy.
constant pressure, right?
Diesel engines, which have been serving mankind for over a century, are the most versatile and economical IC engines. To release the chemical energy in diesel effectively, an atomized form of the fuel is made to contact with high temperature and high pressure air. This energy is effectively transferred as mechanical rotational energy. So the operation of a diesel engine is all about producing high temperature and high pressure air continuously. We will see how this is achieved in this video. Piston, connecting rod, crank, and cylinder form a mechanism called slider crank mechanism. Here, the linear motion of the piston is transformed to a rotary motion at the crank. In an IC engine, this mechanism is properly supported in an engine block. Cylinder head, valves, and fuel injector are fitted above the engine block. When the piston moves downwards, inlet valves open and fresh air from outside is sucked in, or, in other words, the engine breathes. During the return stroke, inlet and exhaust valves are closed, and the air inside the cylinder gets compressed. During the compression stroke, the piston does work on the air, so the temperature and pressure of the air will rise to a level which is higher than the self-ignition value of the diesel. an atomized form of diesel is injected into this compressed air. The fuel gets evaporated and undergoes an uncontrolled spontaneous explosion. As a result, the pressure and temperature rise to high-level values. The high-energy fluid pushes the piston downwards. The hot air does work on the piston, and energy in the fluid is converted to the mechanical energy of the piston. This is the only stroke where the piston absorbs power from the fluid. Due to inertia of the system, the piston moves upwards again. This time, the exhaust valves open and the exhaust is rejected. Again, the suction stroke happens. This cycle, which has a total of 4 strokes, is repeated over and over for continuous power production. You may have noticed that a bowl is provided on top of the diesel engine piston. During the compression stroke, this bowl helps produce air that is rapidly swirling. Thus, the injected fuel gets mixed with the air effectively. The mechanical design of IC engines, particularly that of diesel engines, is a challenging and interesting task. Since the combustion process in diesel engines is never uniform and smooth, they are prone to more vibration and noise compared to petrol engines. Thus, diesel engines require a rugged structural design. Out of the 4 strokes, it is only during the power stroke that a tremendous amount of force is exerted on the piston. So a single-cylinder engine will always have high force non-uniformity as shown. Similarly, the output power will also have a fluctuating nature. But with more number of cylinders, one can overcome these problems. Consider this 4-cylinder engine. Here, 4 different strokes can occur at a time.
Oh, you see that?
So the power stroke is always present in the engine. As a result, a 4-cylinder engine will have better force and power uniformity. In short, the more cylinders an engine has, the smoother it will operate. A 4-cylinder engine generally operates on the following firing order.
Three, 4, 2, 1. So they're offset from each other so that you
A
always
heavy
have
flywheel,
minimum
which
power.
acts like a power reservoir, further helps in smoothing out non-uniformity of power. A huge unbalanced force arises in the form of dynamic unbalance due to the excessive mass at the connecting rod side. This is negated by providing counterweights on the crank side. Opening and closing of valves are accurately controlled by a pair of camshafts. Camshafts derive motion from the engine. It is clear that the camshafts need to rotate at half the speed of crankshaft. We hope you had a nice introduction on the working of diesel engines. Thank you.
Wow. Nice.
So there's no spark in a diesel engine?
It looked like there was.
An internal combustion engine transforms the chemical energy.
I thought there was. You saw the fire going, but
Because it said it would just mix the diesel with the air and that made
maybe
it.
that caused it. Could be. I would have to look it up. Yeah. So many good videos on it, you know. And then, if once you have this learned the thing, the basis for learning all this, you can go to the videos and then fit them into what's going on with the engine, the PV diagram. You get a lot, such good understanding of what's really going on. Then start fixing up cars on the side. So there's so many other cycles. What is this one? Atkinson. Before inventing the Atkinson diet, he would work on this. It seems like this one is kind of dead. Okay, so rather than saying, oh, you have to remember all of this, if in a test type situation, I would give you the numbers. I would say you have a certain gas, and then you could start kind of anywhere. Then I would ask you a bunch of questions based on that. And then in the description of the problem, I would already tell you what is happening. So let me do a sample problem. So let's take, for example, let's say the problem is asking you about the diesel cycle. So it might say something like this. So what is the efficiency of the engine? So what I've described there in words is the the diesel cycle. 20 moles of a diatomic gas at pressure 1.2 atmosphere. So something like this, 3.5 liters. Atmosphere. Compressed adiabatically. So you get here all the way to 1.4. But the pressure is not given right here. So all the way to 1.4 liters. Then the gas expands isobarically, like this, to a new volume, which we don't know, right? Then it expands adiabatically back to its original volume. And then the pressure drops isovolumically. So remember how the diesel one had adiabatic, and then isobaric adiabatic, and then isovolumic. And the pressure drops isovolumically. So then we can say the first stage, second stage, third stage, and then fourth stage. Okay, and then we can find the heat for each stage and the change in internal energy and the work by the gas. So let's see what else is given. The initial pressure is 1.2 atmospheres. We're told the number of moles is 20. And the initial volume is 3.5 liters. Okay, so from there we could do some calculation. Let's find out the initial from the ideal gas law, PV is nRT. The initial temperature, right? P is going to be 1.2. For this one, since already the pressure is given in atmospheres and the volume is given in liters, we can just use the R, the 0.08214 version. 0.08214 to get the temperature.
That will be on Kelvin, right?
Yep. Wait, that cold?
Yeah, right, like a 2.5.
That's let's see what's wrong with this one. 3,000. Why is it so cold? Let's see, 20 moles. If it's a volume, it's 3.5, 1.5 atmospheres. Oh, it's telling us that if the volume was only 3.5 liters, the pressure should have been a lot higher for 20 moles of gas. Let's see. So I guess we could say 0.2 to make it more realistic. 0.20 moles. So then it'll be more realistic number, 255 point. 0.66 Kelvin. Okay, that's better. Okay, so now you know the temperature here, 255.66 Kelvin. Okay, now let's do the stage one. Since it's adiabatic, QE to the gas is 0. And then what's going to happen? The work done by the gas, since Q is equal to W1 plus delta E1, W1 is going to be negative delta E1. Okay, so the work done by the gas is going to be the area under this graph, right? Or the other thing we need to do is find out over here what pressure it's going to reach, right? Since it's adiabatic, so we have P, P2, V2 to the gamma is P1, V1 to the gamma, right? So P1, V1 to the gamma, P2, V2 to the gamma. So this is 1.2 atmosphere. And then this is 3.5 for V1. The gamma of a diatomic gas is gonna be what? So if you forgot, you just say CV of diatomic is 5 halves, CP is 7 halves, so gamma is 7 halves R over 5 halves R. 7/5, 1.40. So just like with air is primarily diatomic, gamma is 1.4. You'll see. So to the power of 1.4. So P2 and then V2 is going to be, it's already given, 1.4 liters to the 1.4. That one, we don't have to change it to meter cubed. We can keep it in liters. So just take the ratio of that. So then it's going to be 1.2 times. What you could do is just take the ratio of 3.5 to 1.4 and then raise it to the power 1.4. So 1.2 times parentheses 3.5 over 1.4 close parentheses to the power 1.4. So P2 came out to be 4.328 atmosphere. So the pressure went really high, all the way from 1.2 to 4.328. 4.328 atmospheres. Now we could also calculate its temperature. Okay, so at every corner, calculate pressure, volume, temperature, all the state variables. Okay, so now if we have the pressure, so we can say, change that to 4.328. And then the volume, change it to 1.4. Okay, calculate the new temperature, T2. Okay, T2 is going to be 368.84. Okay? So then, now we could say, what's the work done by the gas there? Well, the gas is gonna do negative work, right, because you're compressing it. So then, okay, so the work done by the gas is gonna be integral PdV, and then PdV, remember PV to the gamma is a constant. PV to the gamma is P1 V1 to the gamma. So then P is just gonna equal P1 V1 to the gamma over V to the gamma. In other words, you wanna know how the pressure is changing as a function of volume. And so you use the fact that the ratio of PV to the gamma is a constant. So pressure is P1 V1 to the gamma, which is some constant value, divided by V to the gamma. So then you can say P1 V1 to the gamma, dV over V to the gamma from V1 to V2. And that's the work done by the gas. P1 is gonna be, now I'm gonna change this to pascals. So it's 1.2 atmospheres. So I'm gonna change 1.2 atmosphere, but each atmosphere is 101.3 times 10 to the 3 pascals. Each atmosphere is 101.3 kilopascals. So that's the pressure. P1. V1 is gonna be the volume in meter cube. So then that's gonna be what? 3.5 liters, but 1,000 liters is 1 cubic meter, right? So 3.5 liters, 1,000 liters is 1 cubic meter. And now raise this to the power 1.4. Which is this one. Now the integral of this is gonna be what? V to the minus gamma plus 1, right? V to the minus gamma plus 1 over minus gamma plus 1 from V1 to V2. Okay, so then what's this portion gonna be? We can just focus on the integral portion. This one is gonna go 1 over, I could switch the order of this, gamma minus 1, and then switch the order of the integral. So put this one first. 1 over V1 to the gamma minus 1 minus 1 over V2 to the gamma minus 1. In other words, if I would have this smaller value of V1, one over gamma minus 1. Yeah. So then if I put the gamma work by gas 1.2 times 101.3 times 10 to the third times 3.5 over 1,000 to the 1.4. 1 over gamma is 1.4 minus 1. Then I have 1 over V1 is gonna be 3.5, so 0.0. I'm gonna change that to cubic meters by just dividing by 1,000. So 1 over 0.0035 to the 1.4 minus 1 to the 0.4 power.
Should it be gamma plus 1 then?
Huh? I took this and brought it to the bottom.
Shouldn't be minus gamma minus 1?
Yeah, gamma minus 1. Yep.
No, like minus gamma minus 1.
Minus gamma minus 1. You mean this should
Yes.
stay as a minus and this turns to a minus?
Yes.
No, but if you flip it to the bottom, like 2 to the power negative 2, 1 over 2 to the 2. So 2 to the negative 2 plus 1 is 1 over 2 to the 2 minus 1.
Yes. But when we're integrating, I'm confused.
You're integrating v to the negative gamma,
Shouldn't it be gamma plus 1?
negative gamma plus 1.
So negative gamma negative 1.
Huh? No. When you integrate, let's say x squared dx, you get x to the 3 over 3.
Yes.
If you integrate x to the negative 2,
Okay.
you get x to the negative 1 over negative 1.
Okay.
So how did you get negative 1 over negative 1? You do negative 2 plus 1 over
Okay.
negative 2 plus 1.
Okay.
So you see, you get v to the negative gamma,
Yeah, that's confused.
negative gamma plus 1. So this is negative 2 plus 1 over negative 2 plus 1.
I forgot.
Yeah. Then this one goes 1 over negative 1. Then this one goes to the bottom, x2 minus 1. And all those negatives are killers, aren't they? Yeah. So minus 1 over 0.0014 to the 0.4 power. Anyway, whatever you do, the answer to this should come out negative. The work done by the gas should be negative because you're the one doing work on it. So no matter if you make a mistake, you write this before this, doesn't matter, you should get a negative.
That's 0.0014 to 0.4.
0.4, yeah. Negative 470. And so what does that mean? That means the delta E of the gas is negative of the work done by the gas, right? So if the gas is doing negative work, then the delta E is negative of negative. That means the delta E is positive. So it's the same as this, positive 470.878 joules. What if someone was too lazy to do that integral and said to themselves, oh, here's the easier way. I'm too lazy to do that integral, but I know delta E of a gas is NCV delta T, or if it's isobaric, NCP delta T. Right? Can we have gotten the answer that way? And then said, oh, now that in other words, do this first, and then argue that the work is equal to negative of that. Why can't you do that way? So would that work? Let's say you put the number of moles, 0.2, what's CP of a diatomic gas? 7 halves times R. And then what's delta T? Well, we already know the temperature it has here, minus the temperature it has there. So sometimes it does pay to be lazy. Find quicker ways to do the same thing, you know. But let's see if it works.
It doesn't.
It's not even close.
No.
658.
I know, but if we change the 7 half for 5 half, then we got it.
Oh, okay, so basically say, go back
CV.
to CV.
Uh-huh. If we do CV, then yeah, it's for 7.48. Why?
See, this process is neither isovolumic nor isobaric. But delta E should always be able to be replaced by NCV delta T. Let me see, is the 5 halves working?
Yeah.
You're saying?
Yes. Pretty close. It's good.
Well, 470,
So CV.
it helped to be lazy.
But what would be CB?
So we proved something general. Delta E is always replaceable by NCV delta T. The only time we use the NCP delta T is if when you were calculating Q into a gas, and then we say delta E plus PDV, and then when the process is isobaric, when the process is isobaric, then dE is NCV dt, PDV becomes NR dt when it's isobaric. Then we add them and we get what? NCP dt. In other words, we never change the fact that dE is NCV dt. It's always true. dE is NCV dt. The only difference is that we're adding PDV, and PDV is NR dt when it's isobaric. When we add that to this, we get NCP dt. So it's never true that dE is NCP dt. dE is NCV dt. In other words, the definition of CV is the increase in energy. CV is defined as 1 over dE over dt. At constant volume, and when it's constant volume, the gas is doing no work. And so all the heat goes into the gas is equal to its internal energy. Okay? So you want to avoid doing this integral? Okay, be my guest, you could do that. It works.
Professor, why did the gas?
Ha ha! We proved the big thing. So since in adiabatic, work plus change in internal energy is 0, the work is by doing an integral. We don't want to do that integral, we just said change in internal energy, negative NCV dt. And then we can do it that way.
Russ, why did the change of gas turn positive? Change of energy of gas, why the work turned positive?
No, it didn't turn positive, it's just that the delta E and the work are opposite to each other. Because they have to add up to give you 0.
Oh,
Yeah. So a big thing that we did is that you don't have to do that integral. The teacher, I'll talk to her and he'll give you credit. Okay. Okay, so now where's stage 2 now? Stage 2.
Remember when we were in the S-Lab, and you were like, oh, you use that 1.5
What's the dE of the gas? Oh, okay, let's find the pressure, the volume there. Oh, we don't know the volume there. Why didn't the problem give you the volume there? Oh, you know why? Because that's something it can't give you. You have to do another PV to the gamma is constant. In other words, you, oh, you know what? The problem should actually give it to you. Because you could go as far as you want and come back down adiabatically to that volume and then go down. Oh, okay, so the problem should give it to you. In other words, the time when it doesn't have to give it to you, if there was only one specific volume that works. But you could go as far as you want, and then from there come back down adiabatically to this volume, you see? So you could say something like, this volume is, let's say, 2.5. Yeah, so it should give it to you. So it should say, the pressure goes isobarically to 2.5 liters, then comes back down adiabatically. So then from there, we should be able to calculate the temperature there, right? So it would be, let's see, the pressure is constant, so PV is nRT. So then the volume, the ratio of the volume to the temperature, V2T2, is equal to V3T3. So then T3 is going to equal V3T2 over V2. So T3 is going to be that temperature. So it's going to be the volume V3 2.5 over V2 1.4 times T2, which is 368. So that was part of the power stroke, remember? It's like heat is coming in here and heat is coming in there, okay? So 2.5 over 1.4, so times 368.84. 658, oh, really gets hot. 658.64. 658.64 Kelvin. Okay, from there, we can then calculate what the pressure here should be. Because we already know the volume is 3.5, right? So then, okay, let's do the stage 2, and then we can go on to stage 3. So stage 2 is going to be just from here to here. dE is going to be NCV dt. So dB you can always, dE you can always replace by that. 0.25 halves times 8.314 times dt is gonna be 658.64 minus 368.84. Okay, 1,204.71 joules. And then the Q into the gas, or the work done by the gas is gonna equal work by the gas is gonna equal PdV, but then the pressure is constant. So it's just gonna be pressure times volume 3 minus volume 2. So if the pressure is constant, that's the easiest. Just this minus this. Okay, so then that's gonna be the pressure 4.328 atmospheres times 101.3 times 10 to the third. So this is 4.328 atmosphere. Each atmosphere is 101.3 kilopascals. And then change up the volume, which is gonna be 2.5 minus 1.4. And then of course, 1,000 liters is 1 meter cubed. So the 1,000 cancels this 1,000. .27 joules is the work done by the gas. And of course, the sum of the two is equal to the heat into the gas. Q into gas is W plus delta E. This plus that. Plus 12 over 4.71. 1686.97 or 98, let's say. Okay, that's where we can put here a wiggly line. So this is heat coming in. 1686.98. So that's how much heat you're pouring in here. Sum up the delta E plus the work. Here there was no heat because it was adiabatic. Here there's going to be no heat also. Okay. Okay, so now stage 3. Okay, let's find the pressure here and the temperature, right? So then we could say P2, V2 to the gamma is P3, V3 to the gamma. So P2 is equal to 4.328. V2 is going to be 2.5. P3 we don't know, and V3 is 3.5. So the 2.5 was given, so now all we have to do is find that. 2.702. Okay, so that makes sense from the picture because this is 1.2 atmospheres, 2.702 atmosphere. And then the temperature you can find also. So you could say P3, V3 is nRT3. So 2. Let's just do a ratio. P3, V3 over T3, P2, V2 over T2. Since all three of them are changing, I do PV over T is P2 V2 over T. So this is P3 V3 over T3 must equal P2 V2 over T2. All three of them are changing in an adiabatic process. See, neither pressure nor volume nor temperature are the same. So then if I'm solving for T3, cross multiply P3 V3 T2 over P2 V2. So you got to be careful here not to switch any of them to the numerator or denominator. So this is P3, V3, T2, P2, V2. $575.71. 575.71 Kelvin. Okay, that makes sense because it's cooler than here. So this is 368. The hottest point is right here, 658. Then it's cooling. Then it's cooling even more, back down to a normal temperature.
Why do we have to do a ratio? What can we just use this, the PV equals NRT?
Yeah, I guess I thought that ratio might be better,
Oh,
easier.
okay.
Yeah, you could always do also PVs and RT.
Oh, okay.
Yeah. Okay, so then we're left with the Q into the gas. Well, Q is nothing, again, no heat, right? So then, same thing is gonna happen. The work done by the gas and the change in internal energy are gonna be opposite. So since it's cooling, right? So we can say work done by gas is negative delta E of gas in stage 3. And then again, I don't want to do the integral, so then I can just do negative NCV delta T. Okay, so then let's just go 0.2, 5/2 times R, times delta T is gonna be 575.71 minus 658.64. Okay, so 344 joules. Work by gas, and then delta E of gas is gonna be negative 344. And then the last thing to do is just do the fourth stage, the work done by the gas, the delta E and the Q. Okay? So stage 4. The diesel one is kind of nice because it forces you to practice isovolumic, isobaric, and then adiabatic. It'd be nice to have one where it's all 4 processes in one. I don't think we've seen that. Maybe adiabatic. Isobaric. Isothermal. Isothermal, remember, is not as steep as adiabatic, so it would look like this. Adiabatic is steeper. Isothermal, and then isovolumic. So that's like all 4 of them, you know. Adiabatic, isobaric, isothermal, isovolumic. In one of my videos, I have an example where I do, because you don't necessarily have to have one of your cycles be one of these 4. You could do a random cycle. I have a video where I show something like this. Straight line graph, then isobaric, isothermal, isovolumic. And then I say, let's do a complete cycle like that. So you could have any weird thing. It doesn't have to be isobaric, isothermal. You could have a PV diagram, start here, go P is proportional to V to the square function. Then you go down isovolumically, and you go straight line. Some weird thing, and make an engine out of that, you know? Then you could say, well, what's the efficiency of that? What's the heat into the gas? What's the efficiency, you know? So you could start anywhere, go up with any kind of function, do isovolumic, you can go back straight line, you know? Practice something like that in your SI. Not necessarily one of these 4. And then find work done by the gas, which is going to be the integral of that function, right? The delta E, the Q, and then same thing here, and the same thing here. So I believe I have a video on that you can see. Let's see, where am I now? So that one, there is no work because it's isovolumic. So work 4 is 0, and then we got Q into gas is delta E of gas, which is gonna be NCV delta T. And then since delta E is decreasing, right? So that means you're gonna dump the heat back out. 0.2. 5 halves 8.314 times delta T, 255.66 minus 575.71. Negative 1,000. A Q into gas is delta E of gas, which is negative 1,330.45 joules. So that one means you dump the heat back out. See, so always you're putting in more heat than you're dumping, right? So that's always makes sense. Putting in more and you're dumping, and then here nothing is happening, okay? So now if you add up all the delta E's and all the Q's and all the W's, right? All the work done. So the first thing you should check is if you add up all the delta E's, you should be 0. And same thing for if we were doing entropy. If you were add up all the entropy changes, when you come back to the beginning, you should be also 0, because the process, we're assuming the process is reversible so that there's no frictional losses or heat losses. So delta E total, delta E1 plus delta E2 plus delta E3 plus delta E4, okay? So this one, yeah, there was a delta E because it increased, right? Did all the, let's see here, this one heated. All of them experienced a delta E, right? So you went up in temperature, you went up, then you went back down. Oh no, you went down, okay. So these two are positive and these two are negative. So what was delta E1?
470.878.
470 point,
878.
okay. Then delta E2 was
1,204.71.
okay. Delta E3 should have been negative, right?
Yes.
You're cooling back down.
Negative 344.74.
Okay, and then the negative, this one here.
330.
This one's gonna be about 1,680, 1,674, oh yeah, it cancels. Yeah. You put 0 and then you put a happy face like that, always. That means it's working, right? The delta E's cancel. So 1670,
Can you go over
1674, yeah.
the work done negative on the graph again?
Which one here?
The stages, yeah.
This is the work done by the gas is negative,
What?
and then work done by the gas is positive, and then no work.
Okay.
So now we're gonna add up all the work done by the gas. Work done by gas. So then we're gonna have the negative, which is gonna be negative 470. Plus the work done by the gas here. That one I don't remember.
482.27.
480.
482.27.
Plus the work done by the gas here. That one I can kind of follow this and say it's 344. So the gas does 2 positive works and 1 negative work. So the total work done is positive. Okay, now you can calculate the efficiency. The efficiency. Is the work done divided by the heat into the gas, 1686, not the heat that you dump. That's not bad. If you could run it at 21% efficient, that's the diesel car will be pretty efficient then. This was the diesel engine, right? 21% efficient. So that's an example where you are described the different stages of the problem. You're given the starting point, and then from there on, you're just doing calculations, you know, figuring out all the state variables in each corner, figuring out all the heats. Okay, now if we define entropy, bring in entropy into this discussion, and you say entropy is a thermodynamic quantity representing the unavailability of a system's thermal energy for conversion into mechanical work. The unavailability. So the more entropy it has, the more disorder it has, and the more unavailable it is to do constructive work. You see. So often interpreted as a degree of disorder or randomness in the system, lack of order or predictability, gradual decline into disorder, chaos, basically. And the physical quantity known as entropy, we have two ways of writing it, is K ln of omega. Formally, entropy is the Boltzmann's constant ln of omega. So therefore, entropy is going to have the same units as the Boltzmann's constant K. K ln of omega, or sometimes it's also written as K ln of this omega, Greek letter small omega. And then, so the units of entropy are gonna be, this is 1.38 times 10 to the minus 23 joule per Kelvin. So the units of entropy are gonna be joule per Kelvin. So it says, under the assumption that each microstate, let's read from the top. See, here the SI units of entropy, joules per Kelvin. In statistical mechanics, entropy is an extensive property of a thermodynamic system. It is closely related to the number omega of microscopic configurations known as microstates that are consistent with the macroscopic quantities that characterize the system, such as its volume, pressure, and temperature. Entropy expresses the number omega of different configurations as a system defined by macroscopic variables could assume. under the assumption that each microstate is equally probable. You see, the entropy S is the natural logarithm of the number of microstates multiplied by Boltzmann's constant, right? So if I said, for example, you roll the dice and it came out 12, 2 dice, how many microstates will give 12? Just 1, right? 6 and a 6. So the entropy of that will be K ln of 1, which is 0. So if I told you that the roll is a 12, the entropy of that is 1 because there is no uncertainty about that. But if I told you, no, you got a 7, well, that's the most likelihood of getting a 7. You could get a 4 and a 3, 5 and a 2, 6 and a 1, 3 and a 2, right? So there's a lot of possibilities of getting a 7. So that has a high entropy, you see. So things that are very likely to happen have high entropy because there's many ways of that event occurring, you see. So that's what the omega is measuring, is macroscopic system. So it says macroscopic systems typically have a very large omega of possible microscopic configurations. For example, the entropy of an ideal gas is proportional to the number of gas molecules N. The number of molecules in 22.4 liters of gas is roughly 1 Avogadro's number. The second law of thermodynamics states that the entropy of an isolated system never decreases over time. Isolated systems spontaneously evolve towards thermodynamic equilibrium, the state with maximum entropy. You see, non-isolated systems like organisms may lose entropy provided their environment's entropy increases. So we ourselves are entropy decreasing organisms. We take from our surrounding, we use the resources of our surroundings and decrease our entropy so we can make something valuable out of it. But we increase the entropy of our environment, right? Such as global warming, we cause things like that, you know, so we can't necessarily cause just good things to our surrounding. It's wrong, because second law of thermodynamics doesn't permit that. That's why when people say, we are a virus to our society, we should kill ourselves and start over. You know what? That's entropy. Life is, very existence of life is that, is to decrease its own entropy by increasing the entropy of the surrounding. You can't not do that. But we could try to minimize our effect on the surrounding, right? Try to be as good as possible, but you can't do that. We are gonna affect our Earth and eventually maybe find other planets to increase its entropy. For us to thrive and progress, we have to mess something else up. It's in the very law of nature in entropy, you know? So you can't do that. So it says, provide non-isolated systems like us. We are non-isolated. May lose entropy, which we always do, provided their environment's entropy increases. Everybody should read this, all those environmentalists, you know, by at least that amount so that the total entropy either increases. Therefore, total entropy of the universe does increase. Entropy is a function of the state of the system. So the change in entropy of the system is determined by its initial and final states. So this whole topic is very, very interesting, you know, whole entropy thing. Okay, so we have the equation ds is dq over p. In other words, we have two ways of writing the entropy equation. One, focusing on the microscopic states, on number of states, and the ln function. So I've read a lot of books that describe why did they define entropy as a log, one book said is because they wanted to make entropy additive. So if there's omega 1 way of making, let's say there's omega 1, let's say one state can have omega 1 ways of creating that state. And then another thing can have omega 2 states. Then the total omega would be that, right? 10 ways of making something happen, 18 ways of making another thing happen. So there's 180 ways of it happening. So then if you define entropy as log, what's going to happen? Right? So then entropy becomes additive. So if I have two pairs of dice and another 2 pair of dice, and this one I roll and this one I roll, there's a certain number of ways of getting 7 on this, and then a certain number of ways of getting 3 on that, right? So how many possibilities are there? We take their product to get their total number of ways. Well then, that's like saying the entropy of one adds to the entropy of the other. So a log is a convenient way of defining entropy because it becomes additive. The disorder of something plus a disorder of something becomes a total disorder. The other reason why log is good is because if there's only one way of making something happen, then there's no entropy because log of 1 is 0. So it's a convenient mathematical equation. The other equation for entropy is the one we saw on the top. Which is the macroscopic way of defining entropy. It's saying if you put in heat into something over its temperature, the change in entropy is the heat you put in over its temperature. So that one has to do more with the change in entropy. So does that mean the units is still joules per Kelvin? Both ways the units should be joules per Kelvin. Well, here it's K ln of omega, right? So then it would be what? This is the K is units of joules per Kelvin. With this way, it's also joules per Kelvin. You see? So what is this one saying? If you have an object that is at 10 Kelvin and I add 1 joule of heat to it, how much does its entropy increase? 1 joule over 10 Kelvin. So its entropy increases by 0.1 joule over Kelvin. If I have something that is at 100 Kelvin and I add 1 joule of heat to it, how much does its entropy increase? 1 over this 0.01 joule over Kelvin. If I have something that is at 1000 Kelvin and I add 1 joule of heat to it, how much does its entropy increase? So whose entropy increases by more? Something that's cold and I add a certain amount of heat, or something that's already very hot and I add the same amount of heat? Okay, does that make sense then? Something that's very, very cold, such as a 10 Kelvin gas, if I put 1 joule of heat to it, does the amount of information I have about what the molecules are doing, does it increase by a lot? Because remember, one 10 Kelvin gas, there isn't much that I don't know. They're pretty much going very slowly anyway, right? By adding 1 joule of heat, what's going to happen? They're going to start moving relatively quite fast compared to what they were at 10 Kelvin. So now I don't know what they're doing by how much. My knowledge of what they're doing decreased by 0.1 joule per Kelvin. In other words, its entropy increased by 0.1. The information that I have about the system decreased, do you see? By 0.1 joule. It became more chaotic. But now something that's at 1000 Kelvin, I add 1 joule. Am I going to affect it a lot? No, its entropy increases very little. Do you get the idea? That's why entropy is defined like this. Now we can kind of increase this into other things. So imagine writing the first law of thermo like this. How is the law of thermo? The first law of thermo, Q into a gas is delta E of a gas plus work done by gas, right? So now let's write the differential form of the first law. dQ is dE plus PdV. So a certain amount of heat I put in increases its energy, and this is the work. Now I could take dQ and replace it by what? TdS. So I've changed how the first law appears, right? Then I could also write it like this. Okay, now I could define three other state quantities. One is called enthalpy. I think the symbol usually is H. Kind of introducing you to the whole thermodynamics, not necessarily just from physics, but also physical chemistry and chemistry. So enthalpy is a thermodynamic quantity equivalent to the total heat content of a system. It is equal to the internal energy of the system, which is E, plus the product of pressure and volume. You see? Now if I take the derivative of this, what do you get? Right? And then you take the product rule, P times dV plus V times dP. Right, and then you can say, you know what, let's just erase this one. Then we could say PdV is equal to TdS minus dE. So then I could substitute that here, and I could have dH is equal to dE cancel. So, in other words, a unit change in dH is TdS plus VdP. In other words, if I change the pressure, if I change the entropy of a system, then I change the enthalpy of a system. You see? Have you guys used this at all in Chem 102 maybe?
Not yet.
I think Chem 102 does this. Then we could also define something known as Helmholtz free energy. In thermodynamics, the Helmholtz free energy is a thermodynamic potential that measures the useful work obtainable from a closed thermodynamic system at a constant temperature and volume. You see, so they're all kind of interrelated. One is total internal energy, one is entropy, one is enthalpy, one is Helmholtz free energy. They're all, but they're kind of a cycle. Okay, so how is that one defined? The Helmholtz free energy is defined as the energy E minus Ts. This U is another symbol for E, the internal energy. So Helmholtz free energy, I have it as A, different symbols. So I guess we could use their symbol. It's F is equal to, so then it's gonna be energy E minus Ts. Temperature times entropy gives you joules. And then this is also joules. And then this gives you joules. So U and E are the same thing. So now if I take the derivative of that, what happens? dF is equal to dE minus the derivative of TdS minus SdT. Now you're taking the product rule always. And then what are you gonna do? TdS you're gonna say is dE plus P, yeah, you're gonna eliminate one of these here. TdS is gonna be dE plus PdV. This is gonna be, TdS is gonna be dE plus PdV minus SdT. And then the dE cancel, dF is gonna equal negative PdV, negative SdT. dF is gonna, yeah, negative PdV, negative SdT. And then there's Gibbs free energy. And then Gibbs free energy is a thermodynamic potential that can be used to calculate the maximum of reversible work that may be performed by a thermodynamic system at a constant temperature. How was that different from the Helmholtz free energy? Helmholtz was that measured the useful work obtainable from a closed thermodynamic system. And the other one was the maximum of reversible work that may be performed by thermodynamics. So it's G is equal to H minus Ts. And then, so in other words, you see H is defined by energy plus PV. And then once you define H, then you can kind of play with it and you can say, okay, Helmholtz free energy is energy minus Ts. And then this one is enthalpy minus Ts. And then you take the derivative of that. TdS minus SdT. And then the H you can substitute as dE plus PdV. The H you can substitute TdS plus VdP. TdS plus VdP minus TdS minus SdT. So dG G is equal to TdS cancel, VdP minus SdT. So now you, sometimes in thermodynamics books, you'll see something like this. You'll see the definition, for example, the definition of, so we have, where was the original equation? Let's see here. B is TdS. Oh, the original one that I wrote down, remember, was dq is equal to work plus dE plus the work PdV. Then here I wrote TdS is equal to dE plus PdV. So this is the first law of thermo. And then you have dE is equal to TdS minus PdV. Yeah. In other words, what are these? This is 4 different ways of writing the first law of thermodynamics. This is the original way, the internal energy, but then by introducing entropy. So this is the first law of thermodynamics, number 1 way. And then we could say, this is the second formulation of the first law of thermodynamics. Second formulation of first law, okay? This is the primary one with the introduction of entropy. And then we could call this one the third one and the fourth one. Okay? Now, why does this help in any way? Well, what this does is it makes energy like almost like the function of 2 variables, entropy and volume. Okay? So it makes like, this is almost like a Calc 3 problem. Energy is a function of the entropy of a gas and the volume of a gas. Right? So this is the entropy and the volume, and then these 2 are variables. You see? So if we were to graph the energy as a function of, let's say, volume, and keep the entropy the same, at constant, right? Just graph entropy as a function of this, keep delta S constant. What would happen? You would get some kind of graph, right? The slope of that graph would be equal to what? Negative of the pressure. If the entropy was held constant. So what we can say is negative P is equal to partial derivative of energy with respect to volume with entropy held constant. So that becomes the definition of pressure of a gas. Pressure of a gas is equal to how much the energy changes when you change the volume, negative of that, while holding the entropy constant. You see? So we're giving state quantities mathematical meanings by this. So then what's the definition of temperature of a gas? The temperature of a gas is the derivative of energy with respect to entropy while holding what constant? While holding volume constant. In other words, graphing energy versus entropy, right? And as the entropy is changing and the energy is changing, the slope of that line is temperature. Does that make sense? If I keep the volume of a gas constant, pour in heat, the entropy is going to increase and the energy is going to increase. If I divide the energy increase by the entropy increase, that will tell me the temperature of the gas. So if a gas is hot, it will, it's hotter, it will experience more energy increase for every given entropy increase. You really have to wrap your head around that, you know. So what does it mean to say that a gas is hot? For a given entropy increase, the internal energy increase will be more. Or the other way around, you can say, what does it mean to be hot? For a given energy increase, the change in entropy is going to be smaller. That's even better to word it that way. Yeah, because if something is hot and I increase internal energy by a certain amount, the change in entropy is going to be lower if it's a hot gas. And that becomes a definition of temperature, right? And now you could go over here and do that for every other form. You could say temperature is defined as the partial derivative of enthalpy with respect to entropy, keeping the pressure constant. You see? And then volume is defined as partial H, partial what? P, while holding entropy constant. So you see, as long as you're taking derivative of this with respect to this, while holding that thing constant, that thing disappears, and you define this variable. You see? So that becomes definition of temperature, volume, and then you can define entropy and pressure that way too. You can say pressure is defined as partial F, partial V, while holding temperature constant, and then entropy is defined as partial F, partial T, while holding V constant, and then you could do the same with that. So you just get a variety of cases. But I think just this body by itself is already a powerful, just if you focus on energy and entropy, energy and volume. If you hold the entropy constant, increase the volume, and then measure how much energy it's increasing. The ratio of the two should give you pressure. That's what it's telling you. So if you increase the volume, the energy is increasing. The ratio of the two is the pressure. And it should, you know, so try to visualize that and then it should make sense. Okay, when we come back, we're gonna do actual problems with entropy. Variety of different kinds of problems where I'll focus on the TDS. Okay, cool.